Hello, my name is Leonardo Ramirez, and today I will be presenting my argumentative exam. So let's go through that. Let me share you my screen so you can see the processes I used. Here we have them. Let us go through all of them really quickly so we have time. So here we have in the first place the problem of the Newton's law of cooling and heating, where, well, we can, first of all, we have to understand that this is like a ODE. So here we have the analytical solution where we are simply integrating in the both sides after performing some calculations. We have one dt in one side and the other dt in other. So we can keep going. We can integrate both of them. We will end up with natural logarithms, which we can cancel by using the exponential functions. And we end up with this finally. Um, I will also upload this PDF so it can be revised. And well, at the end, we have t minus ta equals to e minus kt times e to the c3. Let's remember c3 is a constant, so for simplicity, we can just put it as c. And we end up with t minus ta equals to ce to the minus kt. If we solve only for t as temperature as a function of time, we end up with our mathematical model which matches the initial solution given in the instructions. So now let's try to understand what is C. We can solve for it in order to discover the meaning. Given an initial condition of the temperature at time 0, we have that this could be represented as T0, where temperature at time 0 is given, by T0. So if we put that in our model, we end up with the exponential function being 1 since it is elevated to 0, and we end up with c equals to T0 minus Ta, which is the difference between T0 and the ambient temperature of the problem. Here we have a heating and a cooling processes, which we can basically just solve by substituting values. We have to substitute the temperature, for example, at 215 seconds. We also have to use that time in order to get K. We also have to use the natural logarithms and the exponential thing. And at the end, we end up with a value for K, which is a proportionality constant. And we can just put that into our model instead of directly K. And we can also find C just by using the T0 minus T8 formula. And here we will have our complete model. Then to solve for time when temperature is equal to 26, similarly, we can only just substitute. And at the end, we end up with time being this result in here, which is nearly 3,251.29 seconds. Here we have the plots in MATLAB. This is directly just the models being plotted. Here we have the comparisons between the heating and the cooling. We can see the heating in red and the cooling in green. And well, as it was expected, they are similar, but in different, like directions, since one it's starts from the ambient temperature and then goes all the way to, I don't know what temperature it was. Here we have the data if we want to check further. But well, that's the comparison we can do. And here we also have Euler's method, which was performed just as in the class activity. Here we have the for loop, we have the data, we have two different Euler's methods, one for heating and the other one, as it is shown here, for cooling. We are also plotting this, and as we can see, the analytical of heating matches with the Euler of heating, and the same way with cooling. I used a different line width for the analytical ones, so we can see that they match, and that's pretty cool. I believe it's pretty awesome. It was expected if done in correct way, but still, I think it's really cool to see. And we can use the different tools that MATLAB give us in order to see it in a better way. And let us go directly to the second problem. Um, we have to first derive the temperature equation. We have that Q equals to mc delta T. And well, we can, well, yeah, we are giving a power and a power of an electric heater. So we have to derive an equation that includes power instead of just Q. And the work done in this case can be equal to Q in the formula of power equals to work over time, as seen in class in some examples. And we expect the time as T equals Q over P. So if we solve for P, we have that P equals to Q over T, which makes sense because Q would be like the work um, done in this case with the energy being transferred. So yeah, let us just, instead of putting Q, let us just, well, we have to solve for Q. And once we solve for Q, we can just replace this in the original equation for Q. And we also replace the delta of temperatures with the final and the initial one. And we are being asked to get an expression for T of T. So we can assume that the final temperature will be this variable goal we are trying to seek for. So if we replace that, and then we also have that P equals to 1000 watts. So at the end, we end up with this equation, just replacing the value of P and solving for T out of P, which would be the final temperature. In this case, we are assuming. So here we have the complete model for T out of T. So yeah, we are including MC, we are including time, we are including the initial temperature. And well, let us see that into MATLAB. It is important to mention that the density of seawater, according to this organization, Woods Height Oceanographic Institution, is this. So in order to find, we are being given the value in liters, but we wanted it in kilograms. So we can use the equivalents for liters and meters cubed. And we can also find directly the mass, which is at the end really near to 0.8 liters that we were given in the beginning of the problem. And let's also refer to this, the specific heat of seawater, which was taken from a document of the University of California in San Diego. And it's this value right here, 3,850 joules over kilogram Kelvin. So let us use those values in order to plot in MATLAB. As it was expected, it follows a linear behavior. And well, we have here the data, we have the vector for time, and it's just a really simple MATLAB script. But now let us go to curve fitting with a polynomial um, function. In this case, we're being asked to use a fifth degree, which following the same process that we did in class. And the matrices notation and the linear regression, and we end up with these coefficients, and this will be the plot of the real linear behavior with a fifth degree behavior. As we can see, they are really similar as expected, but we must just notice that the coefficients are really near to zero. So this suggests that a linear behavior would be the better fit for our data. Let us go to the problem 3, which, well, we are being asked to apply the principle of conservation of energy, and here we are also using the calorimetry principle, relating the Q of copper and the Q of water. In this case, that are the things that we are using. So we can replace this Q using the M, the C, and the delta temperature for each one of those. And at the end, for simplicity, we're just putting the final temperature as this T and the apostrophe. So we can start solving for T. Let's expand the equation. Let us also combine like terms. And in this way, we get a mathematical expression for the final equilibrium temperature. And in order to find a final temperature using our data that we have, we simply just have to substitute. And performing a units evaluation, we have here that we will end up with Kelvins or Celsius. which is totally fine because that's what we are looking for. And this, according to the data that we have in the problem, this would be the final temperature, equilibrium temperature. Sorry, it's near 48 Celsius degrees, so that's pretty fine. Let us go to problem 4, which involves thermal expansion of a solid cone. It's important to derive the volumetric expansion equation directly from the cone volume formula, which we have here, 1/3 of P times the radius squared times height. But the volume equals to the V initial volume plus the difference in volume after the thermal expansion. So similarly as it was done in class and using these right here, R and H, because well, we have a multivariable function. And well, we can just replace that. And we also have here, it's important to notice that delta V equals to V minus V0. So performing the necessary operations, a process similar to the one done with a sphere in class, we get this. And at the end, we have some negligible variables because they are really near to zero. And at the end, we end up with this, where we can just substitute the delta of H and the delta of R for directly the delta in length initial like equation we have for thermal expansion. But of course, derived to the radius and the height, which are the measurements we are using. And after that process, we end up having the V0 and the 3 alpha delta of T. And well, this right here is just like a formula for the volume of the cone. So at the end, we end up with, yeah, here we end up with the 3 alpha V0 equals 3 alpha V0 delta of temperature, which we know 3 alpha is beta. So yeah, that matches the, here we have it. Let me seek for it. It matches the delta V thermal expansion given by the original formula, which applies for every 2D shape. So we already derived it, and in order to simply get values of it and calculate it directly, the delta of V, we just have to substitute values. And that would be pretty much it. Let us go to problem number 5. And well, just directly by looking at the PV diagram, we can see that temperature is increasing in this expansion, which is also denoted by the arrow. It can be corroborated by using the ideal gas law and solve for T. And since we have PV in the numerator as both PV increase, T also has to increase. So that would be like the justification for just directly looking at the diagram. And well, we can see that a straight line matches none of the processes we covered in class. So we have to use directly the integral formula for the work. But going through basis of mathematics and calculus, we know that the integral is basically just the area below the curve. But from a geometric approach, we can see that the area below the curve is, it has the possibility to be divided in both a rectangle and a triangle, as seen in the PV diagram. Here we have the triangle, here we have the rectangle. So if we just basically perform a geometric analysis, we will end up with the expression of the area of the triangle plus the area of the rectangle will be equals to the work. So we can use the pressures and volumes as heights and bases, and replacing, we end up with W equals to 4,800 joules, 4,800 joules. Here we are also making a units analysis, which end up being joules. That's perfectly fine. Those were the units we were seeking for. So yeah, that's pretty much the exam. Well, that's pretty much it. We cover the different problems in a very quickly way, just emphasizing and highlighting the fundamental processes and calculations used. However, I will upload this PDF for further revision. And that's it. I hope you enjoyed it. And of course, I hope I'll be getting a good rate. So yeah, I'll see you around.